Listen closely. This is the story of a faint hiss that ended a grand idea. In the early 1960s, astronomers still argued about how the universe could look ancient and yet unchanging. One camp, led by Fred Hoyle with Herman Bondi and Thomas Gold, defended the steady-state picture. The cosmos expands, but new matter appears just fast enough that on average nothing evolves. Another camp leaned toward a hot beginning, a dense early state that thinned and cooled as space stretched. The debate was fierce, technical, and stubbornly unresolved, until a pair of engineers, a hilltop horn, and a noise that refused to go away changed everything. The device that tipped the outcome wasn't built to test the origin of the universe. It was a horn antenna in Holmdel, New Jersey, designed by Bell Labs for satellite communications. Arno Penzias and Robert Wilson used it as a precision radiometer. Their craft was simple in principle and ruthless in execution. Measure the sky, measure the instrument, subtract the instrument, and repeat until the remainder is the truth. They tuned their receiver around the microwave band, balanced gains with a Dicke switch to cancel slow drifts, and calibrated against reference loads whose temperatures they controlled. They mapped what the Milky Way contributes at that frequency. They modeled how much of the ground might creep in through side lobes. They logged every possible contaminant: sun, moon, atmosphere, cables, connectors, amplifier noise, antenna losses, even paint. After months of accounting, a remainder refused to leave. No matter where they pointed the horn, high, low, away from the plane of the galaxy, toward the cleanest part of the sky, the receiver reported an excess antenna temperature of roughly 3 kelvins. It didn't vary with season or time of day. It didn't care about clouds. It was simply there, uniform, and maddeningly steady. They suspected the obvious culprit, themselves. A pair of pigeons had made the horn their home. Penzias and Wilson climbed inside, cleaned the interior, and scraped away what they politely called white dielectric material. They trapped the birds, drove them far away, and released them. The birds returned. They tried again. Finally, the horn was immaculate, and the excess stayed. The noise wasn't a local nuisance. It came from the sky. 40 miles south at Princeton, Robert Dick's group, Jim Peebles, Peter Roll, and David Wilkinson were building their own microwave radiometer for a different purpose. Peebles had been calculating the consequences of a hot, dense early universe. In such a beginning, photons would fill space and stay tightly coupled to matter. As expansion cooled the plasma, electrons and protons would combine into neutral atoms. Scattering would shut down. The light would decouple, free to coast through space ever after. Those relic photons, stretched by expansion, should now bathe the universe at only a few kelvins. They weren't the first to imagine that glow. In the 1940s, George Gamow, Ralph Alpha, and Robert Herman predicted it, and even put numbers on its temperature, ranging from a few to a few tens of kelvins as assumptions shifted. In 1941, Andrew McKellar inferred a temperature near 2.3 kelvins from the excitation of interstellar molecules, a measurement that made sense only in hindsight. The thread was there. The instrument to pull it wasn't. Dicke's team intended to build that instrument. News traveled by phone. Penzias called Bernie Burke at MIT to ask if anyone knew what an isotropic 3-Kelvin glow could be. Burke connected the dots and sent the word to Princeton. Dicke gathered his team and, according to recollection, delivered a line that was half joke and half verdict. "Well, boys, we've been scooped." He wasn't bitter. He understood the right shape for history. 2 papers, side by side. One would report the measurement, the other would explain it. In 1965, the pair of short papers appeared back-to-back. Penzias and Wilson reported a persistent, all-sky microwave background near 3 kelvins and documented their war on every known systematic. Dicke, Peebles, Roll, and Wilkinson interpreted the excess as relic radiation from a hot Big Bang and sketched the tests to come. The steady-state model allowed many imaginative add-ons, but it did not naturally produce a near-perfect blackbody glow that fills every direction with the same strength. A hiss turned into a fossil of the universe's childhood. Why was that decisive? In the young universe, before neutral atoms formed, the plasma of electrons and protons was opaque to light. Photons bounced off electrons constantly, trading energy and direction so often that the radiation field reached thermal equilibrium. A system like that produces a blackbody spectrum, radiation at a single temperature with a precise shape. When expansion cooled the plasma, enough for electrons and protons to combine, scattering shut off. Photons decoupled from matter and began a straight journey. Since then, space itself has stretched their wavelengths from visible and infrared into microwaves. What Penzias and Wilson measured wasn't local noise. It was the afterglow of recombination, cooled to a few degrees above absolute zero. Holmdel was the opening. The next moves were confirmation and characterization. Balloon experiments and ground receivers measured the background at different frequencies. By the late 1980s, a dedicated satellite, COBE, flew with two crucial instruments. One, a spectrometer, measured the spectrum across microwave to far infrared wavelengths and found a nearly perfect blackbody at about 2.7 kelvins. With deviations so tiny, they became a headline of their own. The other, a differential microwave radiometer, mapped the sky and revealed tiny temperature variations, ripples only tens of microkelvins across. Those ripples weren't random fuzz, they were the fingerprints of sound waves in the early plasma. Pressure and gravity set up standing waves, wavelengths that fit inside the horizon at decoupling formed peaks and troughs in the pattern. The angles on the sky, where those peaks appear and their relative heights, form a Rosetta Stone for cosmology. They encode the density of ordinary matter, the abundance of dark matter, the geometry of space, and clues to the expansion history. The path from Holmdel runs through those maps. WMAP sharpened them and turned speckles into precision numbers. A universe about 13.8 billion years old, spatially very close to flat, with roughly 5 times more dark matter than ordinary matter, and a present dominated by dark energy. Planck refined the picture, squeezed the error bars, and showed that a simple 6-parameter model fits a vast span of data at once. A hiss became a ruler and a ledger. Alternative explanations fail on shape. You can try to add up the glow of all the stars and dust in all the galaxies across cosmic time and smear it into the microwave band, but the sum doesn't make a pure blackbody. It leaves fingerprints, distortions in the spectrum that precise measurements would see. COBE's spectrum found no such scars. Later instruments hunted even subtler distortions from energy release in the first 100,000 years. So far, the sky says no. Steady state wasn't just wounded, it ran out of places to hide. If you want a picture for the physics, think of a fog lifting. Before recombination, the universe was a room filled with thick vapor. Photons could not cross it without being scattered. When atoms formed, the fog cleared. The light present at that moment began a straight flight that has lasted ever since. Along the way, clusters of galaxies nudged it. Hot electrons in those clusters upscattered some of it, the Sunyaev-Zeldovich effect, leaving spectral imprints we now use to weigh clusters and trace structure. Evolving gravitational potentials shifted some photons slightly in energy, the integrated Sachs-Wolf effect, a handle on dark energy. The background is a backlight. The universe writes on it. The background isn't perfectly smooth, and one pattern is huge, a dipole caused by our motion relative to the cosmic rest frame. One side of the sky looks a little hotter, the opposite a little cooler, by a few thousandths of a Kelvin. Subtract that and the galaxy's own emission, and what remains is the primordial speckle. At degree scales, we see the first acoustic peak. At smaller scales, we see secondary peaks and diffusion damping. From the positions and heights of those peaks, we infer that space is very nearly flat. that baryons load the plasma like inertia in a spring, and that dark matter deepens wells that amplify certain modes. Polarization added another lever. The early plasma's scattering produces a distinct E-mode polarization pattern that interferometers and satellites have mapped. Lensing by later structure converts part of that into B modes, which we use to weigh the large-scale web. A primordial B mode from gravitational waves generated during inflation would be a separate signal. Hints have come and gone, complicated by polarized dust in our own galaxy. The lesson is familiar. It's easy to fool yourself. It's hard to fool the sky. There's a practical layer that shows how carefully the original result was earned. The Holmdel system compared the sky to reference loads with known temperatures and switched rapidly between them to cancel slow electronic drifts. Penzias and Wilson measured the receiver's own noise by inserting attenuators and watching how the output changed. They cooled critical components to reduce thermal hiss. They mapped spillover from the ground and the support structure. They measured how much warm air in front of the horn contributed in different weather. They did everything dull and necessary, because dull and necessary is how a remainder becomes a discovery. As the maps improved, the timeline sharpened. The universe became transparent roughly 380,000 years after the beginning, when the temperature fell to around 3,000 kelvins and neutral hydrogen formed. The light released, then, has been stretched to microwaves by a factor of about 1,000, so we see it today as a 3 Kelvin glow. Embedded in that glow are signatures of the sound horizon, the farthest a pressure wave could travel before decoupling. Measure those signatures, and you have a standard ruler that, when combined with galaxy surveys, lets you chart the expansion history and test dark energy in yet another way. Prizes came, but the argument didn't need them. Penzias and Wilson were honored in 1978 for discovering the cosmic microwave background. John Mather and George Smoot were honored in 2006 for measuring its spectrum and mapping its first ripples from space. Awards decorate a story, they don't carry it. The core point is simpler. Measure what the sky gives you, strip away what you add, and listen to what remains. All of this grew from a stubborn, directionless 3 Kelvin excess that 2 people refused to explain away. That's the moral buried in the measurement. Glory often goes to dramatic claims. In practice, progress belongs to patient subtractions. You take the world apart until the remainder embarrasses your theory, and then you rebuild the theory around the remainder. That's how a radiometer on a hill settled a cosmology seminar. Stand at the Holmdel horn antenna today, now a historic site, and look down the wide mouth that once gathered ancient light. Imagine the photons arriving, launched when the first atoms formed, stretched by expansion, brushed by clusters and filaments, and finally turned into a small voltage in a low-noise amplifier. That chain links cosmic history to human patience. It isn't romantic to say that a bit of stubborn noise changed our picture of everything. It's exact. The episode ends where it began, with a hiss that settled an argument. Steady state promised an eternal, unaging cosmos maintained by continuous creation. The sky whispered otherwise. It said the universe has a childhood and a memory, and both are written in microwave light. Engineers heard it. Physicists recognized it. Together, they turned noise into knowledge. And once you hear that background, you never really hear silence again.